Hi, Dr. Revis here with Watch Me Work It, assigning hybridization domains and VSEPR geometry to Lewis structures. So watch me work it. Before we work these problems, let's just review a few basic principles to keep in mind. First, when we talk about hybridization, you're talking about filling uh, geometrical regions around an atom. So you want to fill that geometrical region around an atom. You see it as a 3D atom and it has that space. There is an organized electronic filling of that space. Two, locations. Hybridization deals with S, P, D, and F degenerate orbitals. So whatever those orbitals are. And in fact, they're hybridized, okay, S, P, D, and F orbitals. And so that's the location where we fill these with electrons or atoms, atoms being elements. The third thing is there's a maximum field capacity for each of these locations. In the S, the maximum is 1. You want to be reminded that when we talk about S being a 1, we rarely write the 1. So if you see S, that automatically means 1. You see, okay, so keep that in mind. We rarely write the 1. We most often don't write the 1, frankly. So you have the S, which we have a maximum field capacity of 1. We have P with a maximum field capacity of 3, D 5, and F 7 at the central atom. When we talk about this, we're only talking about at the central atom or the specific atom in question. And the key is this. Those numbers will add up to the number of spaces that are filled. When you fill the S and you need more space, you go to the P. When you fill the P and you need more space, you go to the D. Fill the D, you go to the F. The key factor to consider then is this. The steric group count, what's often called the bonded pair angles when we talk about VSEPR theory. Now, VSEPR geometry is a molecular geometry or shapes. And that's the one that's most often when someone asks what the shape, they're usually asking for the VSEPR shape. However, there is the parent geometry, and that's based solely on the steric group count. Whatever the steric group count is, we count it, and then we assign the parent geometry. So the parent geometry is also occasionally called the base geometry. Now, the VSEPR geometry equals the parent geometry when the central atom has no lone pairs. And you're going to see examples of that. So let's work through some problems so we can get an idea of what we're talking about here. Okay, so let's start with A. Here we have BE with 2 hydrogens on both sides. What we simply do is count. This is 1 and this is 2. Therefore, the steric group count is 2. We're going to go across and do steric count on all of these first. On the next one, we have 1, 2, 3 things surrounding the central atom. Therefore, the steric count is simply 3. We go to C. We ID the central atom, and we count around it 1, 2, 3, 4 items around it. So the steric group count is 4. Case of structure D, the nitrogen, we have 1, 2, 3, 4, 5. Doesn't matter which way you count. It shows us that we have 5 either way. So we have 5 for the steric group count here. And the next one, we have the central atom, and we have 1, 2, 3, 4, 5, 6. So our steric count is 6. Okay? Now, let's go down to hybridization. So for hybridization, we need to fill 2 locations. If we write an S, that takes care of one of them. Recall, we don't write the 1s, okay? All right, so we don't write the 1. So if we put a 1 there, we write it, but we don't do that. Get it? So that basically means I fill 1 position with the S. That's the maximum for an S. Therefore, I go with a P, and I put one of these in the P. So I have 2. One of them's in the S, and one of them's in the P for SP hybridization. The numbers across the top, if we add them up to 2, and that's our hybridization. So this compound A is SP hybridized. Let's go to the next one. We have a steric group count of 3, so we put 1 in the S, and we have 2 more to fill. We put those 2 in the P, This is 1 here. I'm just going to write this 1 so you can see it. Only so you can see it. We don't do it this way. But that would give us 3. So I want you to be able to see that. So for this, we have sp2 hybridization. Okay? For the next, we have 4 locations. 4 locations we have to fill for this hybridization. So we'll fill 1 in the S, and we could put 3 in the P, and look like we max out that P, and we have an SP3. Again, there's 3 in the P and plus 1 in the S, but we don't write the 1, and that equals to the 4. Next, we move on, and so we have 5 to fill. We have S, there's 1, P, we'll max out at 3, there's 3, 4, we need 1 more D, we just don't write the 1s. Okay? So if we add the numbers across the top, I'm just going to put these numbers in just so you can see it. This is just so you can see them. That adds up to 5. This is sp3d hybridization. All right, so next one, 6. You'll get the hang of it now. It's sp3d2. There we have it. Okay, let me clean that up just a little bit for you. All right, let's make that look a little better. There we go. All right, so let's go down to the domain. To assign a domain, you basically would go back and take a look at your steric count. And what you want to do is assign A is a central atom. I'm going to write that somewhere else for you so you'll have it. Let me write this up top here. A equals a central atom or element. When we say atom, we're not talking Avogadro's atoms, we're talking about elements. So that's A is a central atom. Let's clean it up just a little bit there. I can write even better than that. Central atom. B is the bonded group. Okay? And E, lone pairs. And note the word is pairs. Okay? It takes 2 to be a pair. Note that ABE is the same as AXE in sum. So this would be an X the way some like to write it. I use the B because I like to emphasize it's bonded. Okay, so here we go. So here's what we're going to do. We're going to locate the central atom. You never count the central atom. The central atom's A. It's just written. B, and you ask how many bonded groups do I have to this? I have 1, 2. And there we go. So we have 2 bonded groups, so it's A, B, 2, and that's it. I do not have any lone pairs on this first one here on A. No lone pairs, so it's A, B, 2. All right. This 2 is often written as a subscript, never as a superscript. Okay. But for teacher purposes, oftentimes we'll just write it in a row so it can emphasize the value. All right. So here we have in the next one, in B, we have an A, central atom, B, bonded group, 1, 2, 3 bonded groups. So that's A, B, 3. Someone say, what about the lone pair on the chlorine? Well, they don't count. They're not part of the bonded structure to B. That is, they are not directly bonded to B. We only want to know what fills the space around B. And that's a hydrogen, and a chlorine. Okay? So there we have that. All right? Next, we'll go to 4. So this is A, B. These are all single bonds, by the way. This particular slide is dealing with only single bonded around the central atom. So this just goes right along and say AB4. 5 is going to be AB5 because they're all single bonds. So we don't really care about the electrons around there. By the way, electrons will contribute to distortion. But in this case, we only want to do the domain. A, central atom, B5. 6 is A, central atom, B. How many bonded groups? 6. And there you have it for that. Now, the VSEPR geometry is simply memorization. It is pure memorization. Oftentimes, it's talked about in different fashions, but this is just basic memorized geometry. You get it? There is method to the madness, but it's all memorized. So I'm just going to tell you what I memorized about these. That's it. Nothing more than that. This is linear. AB2 is linear. AB3 is trigonoplanar. I'm going to abbreviate and say trig planar. You'll see me abbreviate these as we go. Pure memorization. Number 4 is called tetrahedral. You'll often see me just write tet later on. tetrahedral. I'll try to spell it out for you now. Getting close. And AB5 is plain trigonal pyramid. I'm writing over this. And when we get to the last one out here is octahedral. You'll have to rewrite those and write them really nice and neat yourself. All right, and then the parent geometry. Parent geometry is going to be exactly the same. These little lines mean the same. When there are no lone pairs, okay, no lone pairs, they have the same names. The VSEPR and parent name are exactly the same when there are no lone pairs. All right, so let's go on to the next one. This one we'll go ahead and move through it pretty quickly. We want to show you what happens when you have multiple bonds. Well, you'll use the same process. We're simply going to count. So let's count. Steric count around the central atom carbon, 1, 2. Count around the carbon here, 1, 2, 3. So what about these bonds? What about them? What about these bonds? What about them? They do not count the items or the attachments to the central carbon. I have one item attached here and a second one attached here. Double bond doesn't matter. Could be triple bond, doesn't matter. Could be 4 bonds, doesn't matter. The items around the central atom are 1, 2, 3, therefore my steric count is 3. If I go here, steric count, I ignore the bonds. I simply see what's on the peripheral. 1, 2, 3. I see 3 things in that peripheral. If I go here, I see in the peripheral is 1, 2, 3, 4. I am completely ignoring the double bonds. They don't count when it comes to the steric count. There's 4. So here, wait a minute, we have double and single. What do I care? I don't. 1, 2, 3, 4. 4 around there, and therefore we get 4 for the steric count. Therefore, to do hybridization, I don't care where the bonds came from, what they look like. I care about, well, I actually do care, but the point is this. I look at the steric count and then I start to assign my hybridization. Okay, so when I look at my hybridization here, I see that this is SP hybridized because I have 2 items to account for, 1 and 2. Here, this is SP2 hybridized because I have 3 events to account for. Just show you this one more time, and then I'm just going to keep going. That gives me SP2. So here we have 3 of these. This is going to be SP2 because I count for 1, 2, 3 items. Here, this is SP3 because I count for 4, and this is SP3 as well to account for 4. This is 1 plus 3 equals 4, SP3 hybridized. The domain here, I write first, A, that's the central atom. How many things around it? 2 things. They're all bonded things, so they're B. That's a B2. Here, central atom called A. That's all A means is a central atom, A, and there can only be one A. It's never A2 anything. It's always A. A, and around it, I have 3 bonded things, no lone pair. So AB3. Here on this one, the central atom, sulfur is A, and I have B. How many B's around it? 1, 2, 3. In this case, I have A, and here I have B. How many? 1, 2, 3, 4 things around it. In this case, I have A, central atom of phosphorus, 1, 2, 3, 4, A, B, 4 things around it. And therefore, we can go back, we can assign the geometry to these, all right, and the parent geometries and the VSEPR geometry in this case will be the same. So we'll just quickly do this is linear. We'll do a couple of these here. And at some point, we might just stop doing these, but why not do them now? Linear, and this is trigonal planar. I will abbreviate. These are both the same, so let me just write it here. These are exactly the same. And so here, this is going to be, again, trigonal planar. And here, this is going to be tetrahedral. And guess what? This is also tetrahedral. Now, just for note, this oxygen, because of its bonding character and the other atoms that surround the phosphorus, the bond angle here might be a little different than the bond angle here, but it's still tetrahedral. All right. And the bond angle is influenced by the bonding and the lone pair surrounding the other atoms. Okay. So let's do one now where we have lone pair. Okay. For the lone pair considerations, we use the same process. But in this case, we're going to count lone pairs as well in this steric count. So here we have 1, 2, 3, 4 items around it, because this is an item, this fills up a region, and this fills up a region. If it fills up a region, it gets counted, and that is 4. In this case, we have 1, 2, and a third one here. So we see the steric count here, okay, is going to be 3. Okay, 2 bonded groups plus 1. So this is a 2 plus 1 bonded group here. This is a 2 plus 2 here. So we go to the next one. Here we have what? 1, 2, 3 bonded groups plus 1 lone pair. Okay, plus 1 lone pair. Clear that up a little bit for you. And that tells me I have 1, 2, 3, 4. 1, 2, 3, 4. So I have 4 groups around this. In the case of N here, I have 1, 2, 3, 4, 5. Can you see that? 1, 2, 3, 4, 5. So this is going to be 5 bonded groups. And here I have 1, 2, 3, 4, 5, 6. Doesn't matter how you count them. It's 6. So I need to count for where they're located in the hybridization. In the case of the first one, there's 4 around it. 4, that means I have SP3, because these numbers at the top must add up to 4. All right. In the next one, I have 3 around it, so this is SP2. In the next one, I'm back to 4 groups around it, so the hybridization is SP3. I just counted for 4 groups. Let me show you. That's 1 plus that equals 4 for SP3. In the case of 5, I fill up the S with 1, P with 3, so that's 3, that's 4. I need 1 more, therefore it's D. In the case of 6 things around it, fill up 1 in the S, 3 in the P, and then I put 2 in the D. These numbers on top add up to 6 for my steric group count. So when we do the hybridization, we'll count in this case for the lone pairs because they occupy space, and we're only concerned about the central atom. All right, and these occupy that space, and I count it. All right, so what about the domain names? Now, we always write A because that's the central atom. In this case, the central atom is sulfur. And around sulfur, I have 2 bonded groups, yes, and I have 2 lone pair. E stands for the lone pair, okay? So we have E equals the lone pair. In the next one, here, NO2, I have A for the N, B for one of the oxygens, 2 oxygens, and the lone pair is E. In the case of the compound M, we have A for the central atom, we have B with a 3, and we have 1 lone pair will be an E. For the next one, right here for N, we have the central atom's chlorine, yes. A for chlorine, central atom, B for 3 fluorine groups, and E with a 2 for 2 sets of lone pair. And now, for the last one over here, we have A for the central atom, and we have 4 bonded groups. In this case, it's fluorine, and 2 lone pair. And we get this for the hybridization. Now, since we have lone pair, the parent group and the VSEPR geometry group will not typically have the same name. There's a couple exceptions to that. Okay? So expect a change in the parent geometry and the VSEPR geometry when we do this. So let's go ahead and do, first of all, the VSEPR geometry. VSEPR geometry is the most common one people ask about, and you just want to know the shape. So in the case of the first one, this was called bent. Another name is called angular. You will see me use bent the rest of the way, okay? But it's angular as well, all right? So here, the next one is not the same bent, but it is bent also. That's simply the name that someone decided to assign it to. The next one here is going to be trigonal with a pyramid, pyramidal. And the next one is something, again, purely memorized. The next one's called T-shaped. And that's a matter of just simply memorize. Nothing magic about it all. Memorize it. And then the last one is going to be called square planar. And again, purely memorized and just work backwards. This sits on an octahedral parent. This one here sits on a trigonal bipyramid, purely memorized, and you can look up spelling. And here, this one sits on a tetrahedral, and this bent one here sits on a trigonal planar, but this bent sits on a tetrahedral as its parent. Okay, and so that's how you do it. All right, how we assign hybridization, domain, geometry, and a few other features you want to know about VSEPR structures.